Welcome to a single tutorial on the subject of inequalities. So before we get into this topic, it's going to be helpful for us to remember the number line. So let me just draw that as a sort of preparatory step here. If you haven't seen the tutorials on numbers, you might find them useful, hopefully, unless you're very comfortable with the different kinds of numbers that we deal with in maths. But there we talked about the number line. This is the set of real numbers. Here's 0, right in the middle. And for our purposes, let me just label a few integers here. Oh, there we go. 1, 2, 3, 4, 5, and so on, and then in this direction, -1, -2, -3, -4, -5. There we are. So just a quick little sketch there of the number line. Now, inequalities are statements that don't tell you the value of something, but they tell you the range of something. Okay, sometimes they can just be a simple statement of fact as well. So for example, we can say that 5 is greater than 3, and that would be an inequality which just tells us a statement that the number 5 is greater than 3. Literally, the number 5 is more to the right on the number line than is 3. For example, we might have that -4 is less than -1. So -4 is less than, namely more to the left on the number line than is -1. So occasionally you can write a statement as an inequality, but more often, for the purposes of maths, we use inequalities to talk about the range of something. So let's write down an equation and then we'll compare it to a very similar inequality. So let's imagine we're talking about x as a real number, and let's say we have an equation. Let's say x take away 2 is equal to 3. So obviously we can solve this equation very easily, and it tells us that x equals 3 plus 2 is equal to 5, and so the value of x sits at 5. But let's imagine a different a different statement, which is an inequality. Let's say instead of an equation we were to write x minus 2 is greater than 3. So if I add 2 to both sides of this equation, or from the rearranging equation tutorial, you'll know we can just take the 2 across and it changes sign. We'll have that x equals 3 plus 2, namely that x is equal to 5. We can do the same thing with the inequality. So in nearly all respects, inequalities obey the same rules as equations in terms of moving things around. There's a very important difference which I will come to shortly. But in terms of additive terms, it's just the same. We can move the 2 across, or we can add 2 to both sides, whichever way you like to think about it. And we will have that x is greater than 3 plus 2, namely x is greater than 5. So this statement, this equation says x is equal to 5. It gives x a precise value once and for all. This is a different statement. This says we don't know the value of x, but what we do know is that it is greater than 5. It's a bit like, I was trying to think of a metaphor, it's a bit like you have a tunnel through a mountain and the height of the tunnel, say, is 3 meters. And then someone tells you that a vehicle passed through the tunnel. You wouldn't know the height of the vehicle, but you would know that the height of the vehicle was less than 3 meters. So very often in life or in science, you may not know the value of something, but you'll certainly have information which tells you the range of something. And so inequalities can be very useful in what we call bounding values. So this statement says, we don't know what x is, but we do know x is greater than 5. So x is some number to the right of 5 on this number line. So as long as we have additive terms, we can manipulate inequalities just like we manipulate equations. So let's just do another example. Let's say we have 2 times x plus 4 is greater than x minus 1. Well, I want to imagine this was an equation. We would want to solve it by bringing x over here, taking 4 over there. Because these terms are additive, we can do the same thing. So I'm going to bring x this way. I'm going to take 4 this way. So I'm going to have 2x. X comes across, it changes sign. I have greater than. I have negative 1. The 4 comes across, it changes sign. And then I can tidy up. I have 2x take away x is greater than minus 1 minus 4 is minus 5, or negative 5. So the answer, as it were, to this inequality is that x, in this case, is greater than negative 5. Let's just do another example. Let's use a different symbol, because we don't always have to think of the number line always being x. We can choose any symbol we like, actually, for values along the number line. Let me choose t. Okay, let's say we have 3t minus 4 is less than, this time, let's say it is t plus 1. Okay, actually let me have a bit more variety with numbers. Let's say it's t plus 3. Okay, no problem. So we're going to bring t over here, we're going to bring 4 over here. So when I bring the t across, it changes sign. Just remembering our sort of manipulations from rearranging equations. I keep this symbol, less than. I'm going to take the 4 across, it changes sign. And tidying up, I have that 2t is less than 7. And I can just then divide by 2 and taking the 2 downstairs into the denominator, and I will have t is less than 7 halves. Right, so here comes the warning. Here comes the one difference between inequalities and equations. Do you see how in the first 2 examples I didn't have to do any dividing across the inequality sign, because I just had a clean single x, and I could just solve this and say x is greater than 5. Here, by taking 2x take away x, I had a clean x is greater than negative 5. However, with this problem, once I had sort of tidied everything up, I had a number times my variable. In this case, we were calling the variable t. I had a number, 2 times t is less than 7, and I quite confidently and sort of quietly divided by 2 to get t is less than 7 halves, which is correct. However, you have to be very thoughtful and careful when you divide or multiply across the inequality sign. Let's see why that's true, okay? Let's imagine we have an equation. So I'm going to go back to equations first just to show you the difference. Let's say we have an equation that x equals 2. So that's fine, right? It just says what it is, x is equal to 2. Let me imagine multiplying this equation on both sides by negative 1. Because remember, from the rearranging equations, you can do whatever you like to an equation except divide by 0. But apart from that, you can do anything you like, but you must do the same to the left-hand side as you do to the right-hand side. So I can multiply the left-hand side by negative 1. That gives me negative x. And I can multiply the right-hand side by negative 1. No problem. I get negative 2. And this is an equivalent statement. It just says that the negative of x is equal to negative 2. So if x were equal to 2, the negative of x indeed would be negative 2. No problem. Now let's see what happens if we were to be so trusting and wrong, it turns out, with inequalities. Let's imagine we said, well, actually, I'm not even going to take one with a variable. Let's just take the statement 5 is greater than 3, okay? Excuse me. Sorry, I got a frog in my throat there. Let's say 5 is greater than 3, and let's imagine that we can just multiply both sides by -1. We would have, so multiplying by -1 is what we're doing. We would have -5, and let's imagine we don't know any different, greater than -3. That is not correct. Yes, 5 is greater than 3. 5 is to the right of 3. If you imagine that you can multiply this inequality by a negative number and that nothing goes wrong, you're mistaken, because if we do that, we see the result is that -5, we're told, is greater than -3. No, -5 is to the left of -3. So what we learn from this is, boy, we have to be careful. If we multiply or divide an inequality by a negative number, we have to switch the sign, as it were, of the inequality. So in fact, this is incorrect. If we multiply by -1, we can do that, but we have to remember to switch the sign of the inequality, and then we find, yes, -5 is less than -3. -5 is to the left of -3. So if you just learn this as a rule, I don't think it's terribly helpful, because I've said this in other tutorials, maths is not a set of rules. It's not like learning a table of French irregular verbs, It's a logical kind of structure where everything is connected and everything has a kind of a way back to the root of things that we can understand. So when I give you this example of 5 greater than 3 and -5 less than -3, I know that everyone watching can see that, yes, that's true. When I multiply by -1, of course, we have to change the sign of the inequality, because, of course, -5 is to the left of -3. So I think it's not good to sort of learn this as a rule, but to feel it in your bones, to have a complete sense of why that's true. And I was thinking, can we understand this without even resorting to maths and just think about logic? And I think we can, actually. Let's imagine that we had the statement in English, house A is as big as house B. That's an equality between the size of house A and the size of house B. So we can say house A is as big as house B. And we could also say, we could negate both sides, and we could say house A is as small as house B. So sort of negating big and using small instead. It's the same statement because it's an equality. So house A is as big as house B and house A is as small as house B are both correct. However, if we have a comparative, which is sort of what an inequality is, if we say house A is bigger than house B, we can't negate it. We can't say house A is smaller than house B. It's not true, actually. The correct statement is that house A is less small than house B. So if we negate the comparison, if we go from big to small, and there is one larger than the other, we can negate the comparison, go from big to small, but we have to then put in like a double negative. So we can say house A is bigger than house B, or we can say house A is less small than house B. And that's really what's going on here, that when we multiply through by -1, we're effectively negating everything, and just as in English, we sort of have to do a double negative then. We're negating, we have to also flip the inequality sign, we have to negate that too. Good, okay. So, that's fine. Let's see another way to understand this. Another way to understand this is to say that I never want to multiply through by -1. And you don't have to. I think it's a handy shorthand. Alternatively, you could have said, let me take 5 across, and I would have had 0 is greater than 3 take away 5. And then you could have said, let me take the 3 across, and it gets a negative sign, and then I would have -3 is greater than -5. And then you see here that if I read it backwards, it says that -5 is less than -3, which is correct. So when we multiply through by -1, we have to remember to flip the sign. If you really don't like doing that, you can actually get round it by just taking something that's negative and shifting it to the other side. So let me show you an example of that. Let's say we want to solve an equation x plus 1 is greater than 3x plus 2, for example. Just made that up. Now let's solve it two different ways. Let's solve it by bringing this across and taking that across. So we would have x take away 3x, because I'm just bringing it across. Again, it's an additive term. When I bring it across, I'm effectively changing the sign. Greater than, and then I have 2, take the 1 across. Just as with equations, we change the sign. Tidy this up. I have -2x is greater than 1. And then I want to divide by -2 because I'm happy with this rule. I'm confident that if I multiply or divide by a negative number, I have to flip the inequality. So I'm going to divide by -2, and I'll have that x is, and I change it here, less than 1 divided by -2, i.e. x is less than -1/2. So that would be one way to do it, where we're just happy to use this additional rule that because we divided by a negative number, we have to flip the inequality. But let's say that you really don't want to do that, okay? Well, you may have gotten down to here, actually. That's fine. Then what you could do is say, well, I really don't like that rule because I don't understand it, or I think it's arbitrary. I'm very happy moving things across the equal sign. Now let me just take this whole term across. So I would have that 0 is greater than 1 plus 2x, because when you take something across an inequality or an equation as an additive term, we change the sign. And then I can take this 1 across, no problem. So I have -1 is greater than 2x. I can divide by 2, no problem, because 2 is a positive number. Dividing or multiplying by positive numbers is no difficulty. We don't have to worry about the sign of the inequality. It's only with negative numbers being multiplied or divided where we have to swap the sign of the inequality. So here I'm dividing by 2. I don't have any worries about that. I have -1/2 is greater than x. And then I can just read it backwards to see. If I just literally read the inequality this way, it says x is less than -1/2. And of course we get the same answer because we followed a logical set of steps in both cases, and we end up with the same answer. So that's, I think, all I have to say at this level of maths about inequalities. It's an interesting piece of maths kind of compared to equations. It's much less precise. It tells you a range rather than an absolute value. But in science, often you don't need to know the absolute value of something. Sometimes you only need to know a sort of bounding value. Is something greater than a certain threshold? Is something less than a certain threshold? So inequalities can play a very useful role in science for that reason. So we are going to move on to quite a significant sort of mini-series now, which is the topic of quadratic functions, i.e. parabolas. I don't know quite how many there'll be in the series, probably something like 6 tutorials. So it's a topic at this level that every student that I've taught finds tricky, but it's actually a really, really beautiful topic, and I hope that I'll be able to show you how all the many different ideas in that topic are connected, and you see the beauty of the whole topic. So I look forward to seeing you then.